morning session on electroweak interactions. This is Yu Nakama from Nagoya, who will be chairing this session. So we have two plenary talks and three panel sessions. So now we start with the plenary talk. So Matteo, could you share your slides?
Sure. Good morning, everyone.
Yes.
So can you see my slides?
Yes, very good. So the first speaker is Matteo Presilla from INFM Padova. So we'll be talking about the BSN experimental overview. So please go ahead. Sorry, here. So I have to say something. So yes, so Matteo, so I'll give you a pre-warning after 20 minutes from now. So the audience can post their questions on Q&A too during the talk. So please go ahead.
Okay, thank you very much. And thank you very much for the invitation for this very interesting workshop. Today, I'm going to talk to you about some beyond the standard model searches highlight from both the Atlas and the CMS experiments with the run-2 dataset of the LHC. So, okay. So first of all, let's start with some context. We are a couple of years after the end of the run-2 of the LHC. So almost 10 years after the Higgs boson discovery, and we've been able to gather a huge quantity of data, both in terms of quality and amount of the measurement that we had. So everything started with the Higgs detection, and now, as we see here from this little snapshot, we can start targeting for the Higgs production in the near future. And this was possible thanks to both the excellent performance delivered by the LHC, but also from the ones offered and gathered by our very nice detector CMS and Atlas during the run-2. And what we have observed so far is that the standard model picture, so the theory of the standard model is keeps resisting quite a lot. And we have observed a reasonable agreement across more than 10 orders of magnitudes in terms of the cross-section of the processes measurement. And we've been able to pass from the biggest and easier to observe processes from very rare ones like the vector boson scattering processes that made the LHC machine a powerful precision machine as well since how it started. So this is a summary plot of what we have been published with all this run-2 dataset and run-1 dataset. So everything started, as I said, with the Higgs boson discovery and with the standard model and electroweak precision measurement that are depicted with the strand of publication in orange here. And then, as we see, as the time is passing from that data, from the date, we're starting pushing toward the possible exotica and beyond the standard model scenarios publication interpretation that recently, let's say, obtained a good, quite high number of publication, but also confirmed by the high quality of the publication. And we've been able to cover a lot of new physics scenario based on either the strong motivation of the theoretical motivation that we have behind some precise measurement, but also for some more, let's say, wide research interests analysis that span from pure resonances to effective field theory. So the general approach of this kind of searches and our activity was to start from let's say specific exotic searches and to start and became more and more model independent and also let's say being also available to the interpretability of our data thanks also to the publication of the likelihoods. So the focus of this overview will be to the most recent highlights of the brand new result with the full run-2 datasets by the two experiments being some of the, let's say, details of the specific analysis left to the parallel session that I've seen that we have a few here in this workshop. So the very first bullet in our list of recent accomplishment concerns the Resonant New Physics program, which is by definition the most, let's say, rich from the beginning kind of signature-based search. So we are looking for a bump in the invariant mass distribution of some final state where we are measuring and we know and we have to determine specifically let's say the shape of the standard model background, and we are looking for a bump that is promoted and provoked by some new resonance that we are hoping to pump up at some point. This kind of searches we know are typically preferred by high energy scenarios, but also the statistics can offer quite a lot of opportunities to explore in smaller, let's say, couplings and phase spaces. A very common and famous example can be, for instance, associated to the W prime searches. Here we have quite a recent result from the Atlas collaboration, where we see the final state of the W with a tau and a neutrino prompted by a decay of a W prime. So this is the invariant mass distribution of the transverse distribution of the final state. We see here the smoothly failing background as described by the sketch here, described by this red line. We see the beyond the standard model, let's say, signature that we are expecting to bump up here. Unfortunately, we didn't find any evidence. That's why we are studying, let's say, the very tails of the distribution by looking and exploring these very nice events that we have collected, like this one, with the highest mass being 2.83 TeV. Another very interesting field of research concerns the leptoquarks model exploration. We know that the very first hint of new physics may be associated to the B anomalies if they are confirmed. And of course, this kind of scenario can be confirmed and clarified, hopefully by the end of the phase 2, so in the next 20 years. And these particles that carry both lepton and baryon numbers happens to be a really good candidate for explaining this kind of anomalies. So we had quite a wide activity on this field, both from the Atlas and CMS community, as you see from the summary plot on the lower limits from the leptoquarks of various model. And we've been explored several kind of leptoquarks spanning from different masses and couplings, targeting mostly to the third generation, which is the most, let's say, common one in association to the B anomalies. We can produce this kind of particles in several mechanisms. Here I have displayed 3 of this: the pair production, single production, and off-shell production, that are sensitive, of course, to different phase spaces and different couplings. In this page, we see a snapshot of 3 of the most recent results, very interesting ones concerning this kind of models that are pushing the sensitivity towards the preferred B anomaly phase space, even though this is quite inaccessible at the moment, because it's pushing towards the, let's say, the highest boundaries of the TeV scale. We see here, for instance, in the top right plot, a recent result from the CMS collaboration, where we have in straight lines the observation by the pair production and single production of this third generation scalar and vector leptoquarks. In this plot is vector leptoquarks into the final state to a top and a leptonic tau and a neutrino, and also associated to the 2B jets in case of a pair production. Here you see the covered area here is the one excluded and let's say preferred by the B anomalies. So we are doing quite a lot towards this direction. Also, the Atlas collaboration made a huge effort towards this kind of model and pushed the exploration in other phase spaces. For instance, we see on the left bottom plot the case of the pair production of leptoquarks in a final state with a top and a tau and a top and another tau. And we see that we have been able to place some very interesting exclusion limits of the mass of the scalar leptoquarks of the down type versus the branching ratio of these particles to the final state tau at top. And this is very interesting because we have been able to push, in the case of branching ratio equal to 1, the exploration up to 1.4 TeV. Same must be told for these other searches that was also accompanied to other SUSY searches in the final state of tau, leptonic, B jets, and MET. And here also the limit was quite improvement with respect to the previous publication. The very same field of application of this kind of model, so that the very same beyond the standard model scenario, which is targeting to B anomalies, can also be accessed by this kind of measurement that we have been performing with the Atlas collaboration by looking for lepton flavor violation channels. Here you see a couple of results very recently published for searching for the Z decay to electron or a neutrino and a leptonic tau that we see here on the top for the reference for the hadronic decay, and on the bottom for the very recent publication that's going to be published soon in the leptonic decays. This is particularly relevant in the case we are considering some beyond the standard model, for instance, interacting with heavy neutrinos, and we may assist to some, let's say, lepton travel violation prompted by some Z boson in the final state or some Z boson in the diagrams. And we can access for the very first time, because the other kind of low energy experiment targeting lepton travel violation cannot, we can access this kind of very interesting diagrams and put upper limits, thanks also to the, let's say, very sophisticated techniques for discriminating the signal with the supposed to be signal, which is this back-to-back diagram here for the hadronic and this back-to-back diagram here for the leptonic final state, versus the major standard model backgrounds, which are the Z to tau tau or the fake estimate of the W plus jets. The results, we see here a sketch of the table of concerning the combination of these two analysis outcomes. And we see that we have obtained a strongest bound ever, let's say better than a factor 2 than LEP, that was the previous publication concerning this model, concerning this scenario. And we see that we have reached 5.0 times 10 to the minus 6, 6.5 times 10 to the minus 6 for both the channels, let's see, which is a huge improvement. But also it's quite relevant to emphasize that this measurement were mostly statistically dominated, which is the, let's say, major source of uncertainty of this measurement. So for the future, we are expecting much more from this channel. Another kind of really interesting topic concerns the pure searches for heavy resonances that are produced in pair or in triple cases. And here, as you see from this summary plot delivered really recently by Atlas, we have interpreted the searches in this kind of final state that have really complex topologies and complex activities from the analysis point of view to determine the signal from the backgrounds in several models, like extra dimensions in several types, and so for some benchmark models, but also with the more generic HVT models, depending on the kind of couplings that we have associated to the measurement. We're going to see 3 of these examples here, but from the CMS side, for instance, here we have the final state that we have recently accessed with the 402 dataset concerning this kind of production mechanisms. So gluon-gluon fusion, Trellian, a vector boson fusion of particles of spin 0, 1, and 2. In a final state in which we have a reconstructed W, so the reconstructed W lepton candidate, which is the W that is decaying to a lepton and a neutrino, but also we're going to have some final state with a Higgs boson with another W, or eventually also with a Z boson in this VBF topology. The analysis was particularly interesting also for the techniques applied for data-driven estimation of the background and on a signal in several scenarios, but wasn't able to find any deviation likely from the standard model expectation. So we put some really strong constraints in several model benchmarks, as those that I mentioned before. And we see here that, for instance, if we compare this result, this upper limit on the cross-section time branching ratio of a couple of models, we see that we have obtained a limit that is better by a factor 4 to 5 by comparing the expected Monte Carlo, which is the dotted lines here from the previous publications. So another kind of really interesting multi-boson production happening in this search. You see here a really nice event display from CMS, where we have the 3 boson candidate event, where we have a couple of W bosons that are decaying hadronically. So you see here the fat jets, and here you see the remnants of the leptonic decay of the W boson that we have measured and accessed during a search for extended warp beyond the standard model with extended warp extra dimensions in some specific scenarios that we have tried to assess when let's say the boson standard model production is suppressed. And we can have a situation like in this Feynman diagram here, where a KK resonance decays to a radian, and this cascade produce 3 standard model vector bosons in the final state. We have accessed this very complicated final state thanks to the definition of several topologies. You see a couple of here. So the boosted topologies here for the two W's merged in one big fat jet on this other result here. And thanks to this, we got the very, very good accomplishment of the very first limits obtained from a 3-boson resonances at the LHC. And the result is expressed in this contour plot. On the axis, y-axis, we see the mass of the radion, whether on the x-axis we see the mass of the KK resonance. And you see that the mass reach was quite high as well, because we reached up to 3.5 of this very last resonance. The very first one of this trailer on diboson and multiboson resonances concerned this very recent also publication, which has attracted some interest in our collaboration, because this final state was almost uncovered. So we have a W and a gamma in a final state, and we are accessing to the invariant mass of the system by exploiting jet substructure technique, let's say to define some contour region and signal region for well modeling the background events and the signal events as well. And we have explored a huge range of this invariant mass from 700 GeV to 6,000 GeV. We have estimated the background by data-driven technique, as I said before, but we were not able to find any significant deviation from the standard model prediction. And so we started by looking at submodel specific cases, by looking at spin 0 and spin 1 resonances and dividing the analysis by considering a narrow resonance left-hand side or a broad resonance right-hand side. Actually, there was some small excesses in both cases that accounts for 2.8 and 3.1 significance in this kind of channels. But when looking at the look elsewhere effects, so global significance, this importance is going to be diminished down to 1.1 and 1.7 sigmas. Now we pass to another very interesting channel. You may recognize with this particularly photogenic monogen event display from 2017 data measured by the Atlas collaboration. You may recognize a very, very energetic monojet event, and this is the missing transverse energy, stemming as the very famous signature of the monojet, which was quite used in the past, like in the 80s or from the 80s so on, to look for SUSY signature or extra dimension or dark matter productions. We pursued this kind of signature by searching for 3 benchmark models, SUSY, dark energy, and WIMP. And we measured in the beam PT recoil. So this, in this case, is the signal region is the MET invariant mass distribution. With the maximum likelihood fit, we try to obtain some, let's say, deviation from the data, which we didn't find, unfortunately. And we put some really strong constraints on this kind of 3 benchmark models. Although this is beyond the standard model measurement, so we used to say that we are quite, let's say, abundant in the expected uncertainties from the Monte Carlo events. In this case, we were really precise, and the uncertainty in the, as you may recognize in the ratio plot, the uncertainty spans from 1 to 4% in the whole range of the MET, so from 200 GeV to 1.2 TeV. One of the limits that attracted most of our attention, at least mine, was this one from the WIMP simplified model with an axial vector couplings with kind of, let's say, standard simplified couplings that we see here, JQ and GK. And here you see the limits that are translated to this, this plan with the mass of the WIMP, and also to the cross-section, let's say, of the wind neutron scattering cross-section as a function of this wind mass. You see that the result is pretty much comparable, also with respect to wind devoted, let's say, targeting experiments like xenon or lux. The kind of final state that has a lot of missing transverse momenta has been quite often used, and also in this case, to access also to something that we cannot access directly at the LHC. So the decay product of the X2 invisible particles, like to the what we have that in the standard model is the X2 to dineutrinos, but we cannot access them. So we are putting, by constraining this, the very same distribution, some upper bound in the branching ratio of this decay, which is 34%. Which is a very good accomplishment, considering that this is just a single analysis, and that in the past there has been quite a lot of interest and a wide, let's say, analysis efforts from both the collaborations targeting to this final state, put stronger and stronger limits on the upper bound of this branching ratio that now has reached with the previous limit that does not include the previous publication and next ones of the next few days, a branching ratio up to 11%. So this brings me, of course, to the part of the SUSY searches, which is something that we are keep pursuing quite a lot, even though the final state we have been covering are quite all that we thought of during the run 2 of the LHC. But the analysis in this case are really complex, being the final state defined by several signal regions, split and depending on the final state. Here in this case, we see a Chargino neutralino search for a final state with 2 B tags, 1 lepton and main transverse energy. Here also we had a really good agreement of our measurement and good timing of the Monte Carlo predictions, but we didn't find, let's say, any deviation from this. So we put really strong constraints in the invariant mass, in the plane spanned by the masses of this SUSY particles, which is stronger than what we had in 2016 by something like 300 GeV. And it is worth to mention that this kind of measurement was mostly, let's say, that the improvement was mostly driven by the 2-jet and boosted region, which was something that we did by some analysis studies.
Matteo, just to inform you, 20 minutes have passed.
Okay, thanks a lot. So I'm approaching my conclusion. Indeed, this part concerns conventional signatures, which should deserve itself an independent talk. And this is basically something that we try to access now and for the future will be more and more important. So searches for let's say the smaller couplings and radius processes in the displaced lepton, displaced vertex, and something that let's say standardly we cannot access to our detector acceptance. We have been trying to maximize it by custom triggering, reconstruction, and detector algorithm, and let's say to go against what we used to do at the beginning, and we obtain really strong limits on the for instance, you see here with the summary plots on the long-lived chiral particles, but also very interesting searches in the case of displaced leptons. So if we look, for instance, at this kind of search, we have been looking for SUSY particles with a gravitino in the final state, and prompted by a lepton decay. And we see that in this case, for this particular signature, we're gonna have some long-lived SUSY electron that is gonna be outside the common acceptance of the detector. So what we did is that we ignored the tracks within something like 10 millimeters to extend the detector acceptance. And we, as you see here from this purple dots with respect to the blue ones, we increased quite a lot by a huge factor the efficiency of let's say taking into account the signal events with respect to a standard technique, and the results are also quite astonishing from the point of view of the phase space analyzed. So another very interesting searches for long-lived particles comes to this very, let's say, extreme signal region explored, which is this one looked during the empty bunch crossing time by the Atlas collaboration. In this time, we are looking for a signal that is propagating through the detector and let's say releasing some energy deposit during the time in which there is no proton-proton collision. Thanks to a really fine control of the background events, which are mostly coming from cosmic muons and cosmic backgrounds, we've been able to catch this upper bounds, which span in an enormous range of particles lifetimes up to 3 years, for instance, which is quite astonishing. And I think that this brings me to my very last analysis overview, which I wanted to pay you some attention on, which concerns, even in this case, some displaced final state. In this case, we have displayed dimuons, but with the CMS collaboration, we have used the scouting, the special trigger that allows us to access to smaller and smaller dimuon mass events, so up to 2 times the mass of the muon, by, let's say, gathering and triggering events with a different rate and considering and saving different event size. So less information, but more useful for accessing this parameter space. And we've obtained no deviation from the standard model, also in this case with the scouting data, but really good insight on this kind of benchmark models for let's say dark photons in a couple of cases with 2 different mixing scenarios. So this brings me to my real conclusions and with some final remarks. So I hope I gave you some quite full overview of what we have been able to do with all this full run-2 data set. We have tried to exploit maximally all the statistics that we have, but we couldn't find any clear sign of TeV new physics with all the HC data, which is something that may be good at some point. As you see from this summary plot from the CMS and Atlas collaboration, and by looking at the numbers that you see on the bottom, we are exploring really high numbers in terms of the mass, which may be also at some point something like the saturation of the energy frontier that we have, and also saturation of the masses that we can reach. But of course, the future is much brighter because we have a completely new phase with the run-3, thanks to which we can explore the techniques that I shown you before, so long-lived particles and much more from all the advantages that we made by the technological point of view, let's say. But also we can start the preparation for the brighter and brighter future that we have with collider physics that we will have after the end of the LHC. So we're going to assist to a huge amount of statistics with the high luminosity LHC and so on, that maybe after that with new, let's say, phases, FCC, high energy, and so on. So thank you. That concludes my topic.